Swayam Prabha. Digital India. Educated India.
Today we will continue our discussion on analysis of composite laminates which have piezoelectric patches. In the previous lecture we saw a case where the deformation was purely in plane. It was because our actuators were actuated in such a way that it generates only in plane force, and also the composite laminate was symmetric. Now today we will see a pure bending case. Now again the structure is same. We have a composite laminate and the laminate is symmetric. Dimensions are same. This is our x axis, this is y. So this dimension is L and this is C by 2 and this is C by 2, and it is fixed at one end. And if we look at the view along the xz plane, it looks like this. So it has a piezoelectric patch, and again we can assume that it is throughout, but that does not matter. Even if we keep it at a small part of it, the analysis remains same. So let us assume that our thickness of the laminate is TB and thickness of the two patches are TC, and the laminate is symmetric. So this is the differential equation that ordinary differential equation that we derived considering the Rayleigh-Ritz technique. So we are solving it using Rayleigh-Ritz method. Now within this differential equation, these terms are 0. These terms does not come into picture because this is 0 because it is a static problem. The actuation is static, so there is no acceleration, and KIW equal to KWI equal to 0 as before, because since B matrix is 0, symmetric laminate. So we are left with only this equation. So these two equations can be the first equation and the second equation can be solved separately. Now in this case the actuation is purely a bending actuation, so we need to solve only this equation. So solve KWW QW is equal to FW. So now as before we need to make some approximations. So let us go to next slide, and our approximation is W as a function of x y is, the approximation that we make is x square by L square multiplied by QW1. So this is, we can call it phi W1, and this is QW1. Now this satisfies the essential boundary condition. So at x equal to 0, W is 0 and at x equal to 0 dw by dx is equal to 0. So, the cantilever boundary condition is satisfied, slope and displacements at x equal to 0 is 0. Now, we need to find out our kWw. So, k we are just writing it as k because other components of k are not there anymore, and to do that we have the expression as B W transpose multiplied by the D matrix multiplied by B W and its integral. Now, we need to find out this B W transpose, and to find out the B W transpose we need our quantities like kappa. So, kappa as we know is del 2 del 2 W by del x 2, this is del 2 W by del y 2 and this is 2 del 2 W del x del y, and as per the approximation this can be written as del 2 phi W 1 by del x 2. This quantity is 0 because phi is a function of only x. So, again it is a very simplified approximation. We are assuming that the bending the W is function of only x. So, bending is with respect to only the y axis, and this quantity is 0 and this quantity is 0, and this is equal to phi W 1, and also del 2 phi del 2 phi W 1 by del x 2 is, if I just differentiate it twice, it becomes 2 by L square, and this is our BW matrix we can say. And also we need the MPs, and MPs have only one component, and which is this. Again that is an approximation. So, we have only one component of MP which is MXP and 0 0, and we know how to find out MXP, we have done it before. So, finally, if we put everything in this expression, this becomes an integral over x and y zero 0, and then we have D matrix here, and here we have 0 0, and this let us write this as an integral from x and y. So, this quantity reduces to del 2 phi W 1 by del x 2 d 1 1 del 2 phi W 1 del x 2 dx dy, and finally, on being integrated this gives us 4 c. Okay, so, this is dx x generally as per our convention. So, this D matrix many a times we write it as D11, D12, I mean all these A, B or D matrix, sometimes we write it as A11, A12, A16, or we can write it as DXX, DXY and DXS. So, some books you will find you will find these subscripts to be 1, 2 or 6, and in some of the books you may find it to be X, Y or S, and both are same. So, this is our expression for K, and K has only one component. So, let us call it K11. Now we have to find out the right hand side, the force term which comes due to the piezoelectric actuation. Okay, now just to note one thing, this we have been calling MPX, not MXP, same thing. Now we have to find out the force term. So we have Fp is equal to minus C by 2 0 to L, and then we have del 2 phi by del 2 phi W by del x2 0 0, and this is multiplied with this vector MPX 0 0, and we have this. So finally this turns out to be this, and then on being integrated the value comes to be 2 MPX C by L, 2 MPX C by L, and then we can solve the equation and QW1 can come to. So this is again, it has only one component, let us call it Fp1 by K11, and that gives me QW1 to be MPX L square by 2 dxx. So this is our QW1, and then we can substitute QW1 to the original approximation, and that gives us W as a function of x. Now we will solve this similar problem using the Galerkin technique. To do it using Galerkin technique, we need to again make a different approximation, because in Galerkin technique when we are having a purely bending problem, the highest order derivative appearing is 4. So accordingly the approximation has to be changed. So let us approximate Wx as 6 x by L square minus 4 x by L cube plus x by L to the power 4 multiplied by QW1. So this is our approximation now. So this is our phi W1. Now this satisfies both essential and natural boundary condition, which means the geometric and force boundary condition. So satisfies geometric and force boundary conditions. So those conditions are W 0, y is 0. Now del W by del x at x equal to 0 is 0, and then we have del 2 W by del x2, it is a cantilever beam. So at x equal to L is 0, and then we have del 3 W by del x3 at x equal to L is 0, and it has the derivatives up to 4th order existing. So we need to make sure that minimum 4th order derivative exists, because that is the highest order of derivative that would appear in our equation. So the equation is dxx del 4 W del x to the power del x4 is equal to del 2 MPX by del x2, and then we define an error as we have been doing, and the error is dxx multiplied by the fourth order derivative of x w with respect to x minus this, and then we say that we have to multiply this error with phi w1, and on being integrated over the domain, that should be 0. So, let us do that. Now, we multiply phi w1 minus del 2 mpx by del x2 dx dy is equal to 0. So, this quantity would give us an equation, a term where I have qw1, and this would give us a pure force term, and by solving that we can find out our qw1. So, if all these if this entire expression is evaluated, finally qw1 comes to be 5 by 36 multiplied by mpx L square by dxx, and then it can be put in the original approximation and our solution is done. Now, we will solve another problem where we have an antisymmetric laminate. Now, we know that in an antisymmetric laminate our B matrix is, so this antisymmetric laminate is angle ply, it is not a cross ply, because depending on whether the laminate is angle ply or cross ply, our B matrix changes. So, this is x bxs, this is 0 0 bys, this is bxs bys 0, and then we have A matrix, and we know that for any balanced laminate our A matrix has Axs as 0 0 0 0 ASS, and then we have D matrix, and because this laminate is antisymmetric, so our dxs dys are also 0. DSS, and again our structural details remain same. We have a plate laminate which has a dimension of L along the x axis and a dimension of C along the y axis, and if we look at it from along the xz plane, again we have piezoelectric patch at the top and bottom, and the patches are of same property, both material and geometric property are same. So, this is TB, this is TC, this is TC, and this is our x axis, this is z axis. Now, in this laminate, the piezoelectric patches which are put here, if they are actuated even in purely in plane mode, suppose I give same voltage at the top and bottom, then also it would induce some out of plane deformation, because our B matrix is non-zero. So, now because B matrix is because in the B matrix we have Bxs and Bys present. So, it is basically a coupling between the in plane deformation and the twisting. Now, please understand that Bxs, Bxy and Byy are 0, and that is why any in plane loading, any in plane actuation is not going to cause any bending, but it is going to cause twisting. So, here twisting and in plane deformations are coupled. Now, there is no coupling between the in plane normal normal strain components and in plane shear. There is no coupling between bending and twisting, but there is a coupling between in plane normal strain components and torsional strain. So, we need to approximate both u and W and solve it accordingly. So, now let us make some approximation. So, assume u0 as a function of x and y is, the approximation that we take is x by L q u1. So, this is our phi u1, and for W, let us make the approximation to be x square y by L square c, L square c q W1, and this is called phi W1, and we have V0 as 0. Now, in this case, in our approximation for W, we took a y component also, because we expect a twisting to be induced. That is why you have a we do not have a purely x component. I mean Wxy is not just a function of x, it is a function of y as well, and u0 is function of x only. Now, all we need to do is we need to solve two equations. So, finally, in this case the equation would look like this. We will have k I w multiplied by q I plane plus we just wrote the equation in the okay. So, we have to solve two equations here. We have k I multiplied by q I, which we call in plane, plus k I w multiplied by q w is equal to f I, and here we have q w I multiplied by q I plus k w w multiplied by q w is equal to f p f w. Excuse me. So, we have to solve these two equations. So, we need to evaluate these matrices. So, finally, this entire thing looks like this. If we write it in the as per their expressions. So, this is B I T multiplied by B matrix multiplied by A matrix multiplied by B I transpose dx dy, and we have q v1 plus minus c by 2 c by 2 0 to L, then we have B I T multiplied by the B matrix multiplied by B W, please excuse me, transpose should not be there, and then we have dx dy, and finally at the right hand side we have this is multiplied by QW1, and at the right hand side we have minus CY2 CY2 0 to L, and then we have BI transpose into NP dx dy. So, again if we follow the same procedure, this comes to be minus CY2 CY2 0 to L, and then we have del phi u1 by del x 0 0, and we have the A matrix here, and this becomes del phi u1 by del x 0 0 dx dy q u1 plus we have same thing del phi u1 by del x 0 0, and here we have the B matrix, and here we have del 2 phi w1 del x2 0 twice of del 2 phi w1 del x del y. Now, please understand, if we look at the approximation for w, this phi w1, if we differentiate it twice with respect to x, there is a non-zero derivative. If we differentiate it twice with respect to y, there is a 0 derivative, and if we differentiate it with respect to x once and y once, again there is a non-zero derivative. So, that is why the middle term is 0 and the other two terms are non-zero. dx dy, and this is multiplied by QW1 minus CY2 CY2 0 to L, and this quantity is del phi u1 by del x 0 0, and here we have npx 0 0 and dx dy. So, after all these evaluations, this quantity comes to be minus CY2 CY2 0 L. So, here we have del phi u1 by del x axx multiplied by del phi u1 by del x dx dy QE1, we are just evaluating this term, and then we have minus CY2 CY2 0 to L. If we evaluate this term, we will get del phi u1 by del x multiplied by B11, sorry, it is not B11, it would be BXS. BXS multiplied by twice of del phi w1 xy by del x del y and dx dy qw1. Finally, at the right hand side we have minus CY2 CY2 0 L del phi u1 by del x npx dx dy. So, there is one equation where QU1 and QW1 are the unknowns. Next, we have to form another equation, and in that equation would be again with QE1 and QW1 as the unknowns, and that equation would look like this 0 to L, and here we have BI transpose multiplied by BW transpose multiplied by the B matrix dx dy, and this is multiplied with q u1 plus minus c by 2 minus c by 2 0 to L BW transpose multiplied by D multiplied by BW dx dy, and then at the right hand side we have del 2 W1 by del x2 0 2 phi W1 del x del y, but there is no actuation because the actuation is purely in plane actuation. Our piezos are actuated symmetrically with same voltage. So, we can write it here. Pure in plane actuation. Now if these expressions are simplified, this comes to be this 2 phi W1 xy, then we have Bxs phi U1 x dx dy q u1, and then we have minus c by 2 0 to L, and here we have contributions from D matrix, and that is phi W1 xx dxs phi W1 xs plus phi W1 xy, and then we have DSS again twice phi W1 comma xy dx dy, and then at the right hand side we have 0. So, here the derivatives are written as comma with with subscripts, and here it was written as the derivative itself, but again they are same. So, we have got two equations. The previous equation is this. Here I have unknowns q u1 q w1. Next equation is this. Here I have unknowns q u1 q w1, and so two equations, two unknowns. We can solve these two equations. After solving these equations, we can find out q u1 and q w1. So, let us give some number to it. Maybe we call it 1 and maybe we call it 2. So, solving 1 and 2 q u1 q w1 can be found out. So, in this problem it was an antisymmetric laminate. The actuation was a pure in plane actuation. Now, although the actuation was in plane actuation, because of the B matrix being non-zero, we had to solve the two coupled equations. So, we got q e1 and q w1. Each of these u and u0 and w had one term in the approximation. So, after this solution we can find out the constants associated with each of these terms, unknown constants, and after getting these two constants we can again back substitute and find out your u0 and w, and that solves the problem. So, with this I would conclude this lecture. Thank you.